Good afternoon. Yesterday we have seen kinematics and dynamics of robots. Today again we'll see forward and inverse kinematics, but today we'll see how to solve different problems related to 2 degrees of freedom and 3 degrees of freedom. Now, forward and inverse kinematics. Forward kinematic. Now here figure has been shown. Forward kinematics to determine where the robot's hand is. If all joint variables are known, that is, whatever this end effector is there of length L3, we have to determine its position. If we are knowing angles theta 1 and theta 2, we can determine angle theta 3. Now, inverse kinematics. Inverse kinematics means what? To calculate what each joint variable is. Means what position is given to us, that is lengths of different arms L1, L2, L3, and we have to determine the angles theta 1, theta 2, theta 3. Therefore, see here, this is forward kinematics, means joint angles are given to us theta 1, theta 2, theta 3. We have to determine x, y, z, and this is the inverse kinematics. Position is given, we have to determine theta 1, theta 2, theta 3. Therefore, this is nothing but forward kinematics and inverse kinematics difference. Now, here we are interested in two kinematics topics. Forward kinematics, that is angles to position, and inverse kinematics. Inverse means reverse kinematics, that is position to angles. Now we will see forward kinematics, angles to position. What you are given, the length of each link, the angle of each joint, that is L1, L2, L3, and phi 1, phi 2, phi 3. What you can find, the position of any joint, that is its xyz coordinates, p of xyz. I mean, inverse kinematics, position to angles, it is known as position to angles. Therefore, what you are given, the length of each link and the position of some point on the robot, that is L1, L2, L3, and p of xyz. What you can find, the angles of each joint needed to obtain that position, that is, we have to determine phi 1, phi 2, phi 3. Now we just say this is the 2 degree of freedom. Means what? Why it is called as 2 degree of freedom? Because two angles are required to define the position of this robot arms, theta 1 and theta 2. Therefore, let L1 length of link 1, L2 length of link 2, phi 1 or maybe theta 1, theta 1 angle made by link 1, theta 2 angle made by link 2, p of xy, position of end effector in space. This is the end effector. Now this is the L1 length of link 1, L2 length of link 2. This is theta 1, this is theta 2 with respect to theta 1. This is L1 sin theta 1, this is L2 sin of theta 1 plus theta 2. Now what are the x components? X is equal to L1 cos theta 1, link 1. X is equal to L1 cos theta 1. And for link 2, x is equal to L2 cos of theta 1 plus theta 2. See that L1 cos theta 1, L2 cos of theta 1 plus theta 2. That is, we have to resolve this. Now adding above x component, we get x is equal to L1 cos theta 1 plus L2 cos theta 2. L2 cos of theta 1 plus theta 2, equation 1. Now y component, y is equal to, for link 1, L1 sin theta 1, and y for link 2 is equal to L2 sin of theta 1 plus theta 2, link 2. Now adding y components, y is equal to L1 sin theta 1 plus L2 sin of theta 1 plus theta 2, equation 2. Forward kinetics of 2 degree of freedom robot. Now forward kinetics of 3 degree of freedom robot. Why it is called 3 degree of freedom? Here additional angle they have provided, theta 3, theta 1, theta 2 and theta 3. Therefore 3 coordinates means 3 angles are required, therefore it is known as 3 degree of freedom robot. Therefore let L1 is equal to length of link 1, L2 length of link 2, L3 length of link 3, theta 1 angle made by link 1, theta 2 angle made by link 2, theta 3 angle made by link 3, P is equal to xy, that is position of end effector in space. This is the end effector. Now x components, x is equal to for link 1 L1 cos theta 1, for link 2 x is equal to L2 cos of theta 1 plus theta 2, and for link 3 x is equal to L3 cos of theta 1 plus theta 2 plus theta 3. Now adding above x components, we get x is equal to L1 cos theta 1 plus L2 cos of theta 1 plus theta 2 plus L3 cos of theta 1 plus theta 2 plus theta 3, equation 1. And y component, y is equal to for link 1 y is equal to L1 sin theta 1, for link 2 y is equal to L2 sin of theta 1 plus theta 2, for link 3 y is equal to L3 sin of theta 1 plus theta 2 plus theta 3. Adding above y component, we get y is equal to L1 sin theta 1 plus L2 sin of theta 1 plus theta 2 plus L3 sin of theta 1 plus theta 2 plus theta 3, equation 2. Now here they have defined one psi angle, that is nothing but theta 1 plus theta 2 plus theta 3. Inverse kinematics of 2 degree of freedom robot. Now see that inverse kinematic means from position to angles. That is, we can determine angle. Position is given to us, we have to find out angle. Therefore, see that xy, this is desired position, L1 length of arm 1, L2 length of arm 2, theta 1 angle made by arm 1, theta 2 angle made by arm 2. Therefore, we have to determine these values using these expressions, that is cos of a plus b is equal to cos a cos b minus sin a sin b, sin of a plus b is equal to sin a cos b plus sin b cos a. We know that the value of x and y in forward kinematics of 2 degrees of freedom's robot, therefore x is equal to L1 cos theta 1 plus L2 cos of theta 1 plus theta 2, equation 1. Y is equal to L1 sin theta 1 plus L2 sin of theta 1 plus theta 2, equation 2. We can rewrite both equations using the trigonometric identity, that is x is equal to L1 cos theta 1 plus L2 cos theta 1 into cos theta 2 minus L2 sin theta 1 into sin theta 2. Y is equal to L1 sin theta 1 plus L2 sin theta 1 into cos theta 2 plus L2 cos theta 1 into sin theta 2. Now squaring both sides and adding both equations, we get cos theta 2 is equal to x square plus y square minus L1 square minus L2 square divided by 2 into L1 into L2, equation 3. Now using trigonometric identity, therefore tan of a minus b is equal to tan a minus tan b divided by 1 plus tan a tan b. We are getting tan theta 1 is equal to y into bracket L1 plus L2 cos theta 2 minus x L2 sin theta 2 divided by x into bracket L1 plus L2 cos theta 2 plus y into L2 sin theta 2. Now this is the problem. It is desired to determine the value to which the angles theta 1 and theta 2 must be set in order to achieve a certain point in space for manipulator as shown in the figure. The length of joint 1 L1 is equal to 12 inch and the length of joint 2 L2 is equal to 10 inch. The point P which the robot must achieve is defined by coordinates x is equal to 15.7 and y is equal to 12.6. Using reverse transformation method, determine the angles theta 1 and theta 2. Therefore, you just see, first of all, L1 they have given 12 inch, L2 10 inch, x is equal to 15.7, y is equal to 12.7. We have to determine theta 1 and theta 2. Therefore, we know that cos theta 2 is equal to x square plus y square minus L1 square minus L2 square divided by 2L1 L2. Therefore, substitute the values 15.7 square plus 12.6 square minus 12 square minus 10 square divided by 2 into 12 into 10, which is equal to, we are getting the value finally as cos theta 2 is equal to 161.26. Therefore, divided by something which is equal to 0.6719. Therefore, theta 2 is equal to cos inverse of 0.6719, which is equal to 48 degree. This is our diagram. Now tan theta 1 is equal to y1 into bracket, y into bracket L1 plus L2 cos theta 2 minus xl2 sin theta 2 divided by x into bracket L1 plus L2 sin theta 2 L2 cos theta 2 plus y into L2 sin theta 2. Therefore, substitute the values, you will get angle theta 1 tan theta 1 is equal to 15.7 into bracket 12 plus 10 cos 48 minus 12.6 into 10 sin 48 divided by 12.6 into bracket 12 plus 10 cos 48 plus 15.7 10 into 10 sin 48. Therefore, tan theta 1 we are getting it as 0.515. Therefore, theta 1 is equal to tan inverse of 0.515. Therefore, you just calculate what is the answer, then you will find out. Now, this is problem on forward kinematics of 2 degree of freedom. Consider the forward transformation of the joint manipulator as shown in the figure. Given the length of joint 1 L1 is equal to 12 inch, the length of joint 2 L2 is equal to 10 inch, the angle theta 1 is equal to 30 degree, angle theta 2 is equal to 45 degree. Compute the coordinate position, that is xy, of the end of the arm P. Therefore, again, solution or answer given L1 is equal to 12 inch, L2 is equal to 10 inch, theta 1 30 degree, theta 2 45 degree. X, we have to find out x and y. We know that formula for forward kinematics, x is equal to L1 cos theta 1 plus L2 cos of theta 1 plus theta 2, and y is equal to L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. Therefore, substitute the values. L1 is equal to 12 cos 30 plus 12 cos of 30 plus 45, which is equal to 12 into 0.154 plus 12 into cos of 30 plus 45. Therefore, x is equal to 12 into 0.154 plus 12 into 0.9217. Therefore, x is equal to 1.85 plus 11.06. Therefore, x is equal to 12.91 inch. Value of x we found out. Now, value of y. Y is equal to L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. Therefore, y is equal to 12 sin 30 plus 12 sin of 30 plus 45. Therefore, which is equal to y is equal to 11.85 plus 4.65. Therefore, y is equal to 16.5 inch. Now, these are the values of x and y. I think same problem. VSC values are changed. L1, L2 they have given as 10 inch, 10 inch, theta 1 35 and theta 2 30 degree. And by using same equations, we have found out value of x is equal to 10.77 inch and value of y is equal to 15.38 inch. Therefore, this like this, we have to find out the values of x, y, and theta 1 and theta 2 for forward kinematics and inverse kinematics problems. Now, we will see some control techniques used in robot. Okay. Now we will see control techniques, or which are the control techniques used in robots. Now what thing we have to control in the robot? We have to control the speed of the robot, or speed of the DC motor or AC motor or servo motor or stepper motor, whatever different types of motors we have studied. And we have to control force also. Why we have to control force? Because you are knowing that robot is used to pick and place the objects. Therefore, while picking the objects, that end effector or that fingers of the robot should apply, or robots should have to apply force to grip the object and then to place it. Therefore, for that things, that force control is also necessary. Therefore, for that we are having some syllabus, that is control architecture of robots, overview of advanced control techniques such as force control, PID control, adaptive control, and PWM control. PWM control means pulse width modulation control. Now, what is meant by control? Linear control. Control of any system means to apply or exert moments and forces on it so that the system moves or works according to the commanded instructions. In a robotic system also, a manipulator is required to carry out some specified tasks by moving its end effector accurately and repeatedly. Therefore, in this chapter, control laws will be developed where the above joint histories can be input in order to make the robot track the commanded trajectory. In some cases, Cartesian trajectory, that is position and orientation of the end effector, is also controlled by calculating how much moment and force are required to achieve it and correspondingly converting them to joint torques, as any robot is basically moved or controlled by a set of joint motions only. Control of a robot requires the knowledge of the mathematical model of the robot and some intelligence to act on it. Whereas the required mathematical model requires physical laws governing the motion of the manipulator. Intelligence needs sensory devices and the means to act and react against sensed variables. In robot control, individual joints are driven by actuators, be they electric, hydraulic, or pneumatic. The actuators apply force or torque to cause the links to move. Their commands are provided by the control system of the robot that will move the manipulator to achieve the specified task intended by the end effector. Now, this is the schematic diagram of a robot control system. See that this is the trajectory generator or input. Then you are knowing that whenever these robots arms are moving, just was in kinematics. Therefore, they are making some angles, theta. Therefore, that angles are nothing but input to the control system. Then the robot manipulator that is fed or that torque from the control system is again provided to the robot, and then from the output robot, that output theta angle is there. Every time that angle is, whether that angle is reached or not, that feedback is given to the control system, and accordingly that control system drives the robots. Now these commands are based on the control set points generated from the set of joint torques versus time. This T means torque. Note that the joint history is denoted in figure 10.1 as theta d or theta d dot and theta d double dot. That is the desired joint position theta d. Then theta dot means its angular velocity, and theta d double dot means its angular acceleration respectively, are prepared by the trajectory generator or planner. However, due to difficulties in accurate computations of the manipulator parameters, for example, the link lengths, masses, and inertia, etc., and non-consideration of friction, backlash, etc., in the mathematical model, the end effector of the robot will not follow the commanded trajectory exactly. Hence, the actual joint and or end effector positions and their derivatives can be fed back to the control system to find the derivations from the desired trajectory and accordingly to generate corrective force or torque for the joint actuators. The schematic diagram of a robot control is shown in figure 10.1, where theta dot and theta d dot represent the actual joint positions and velocities respectively. Control can be classified as linear and non-linear. The use of linear control techniques in robotics is valid when a robot moves slowly and can be mathematically modeled by linear differential equations. In this chapter with linear control of robots, for the case of an actual robot control, such linear methods are essentially viewed as approximate methods because dynamic equations of motion of a robot manipulator are actually non-linear differential equations. However, the linear control theory forms the basis for more complex non-linear control systems. For many practical applications, the use of linear control systems is often reasonable, as the robot manipulators used in major industries move relatively slowly. But if the joints move fast, the coupled dynamic forces are significant and the non-linearity cannot be ignored. In such situations, complex control algorithms are required. Now, control techniques. Several techniques can be employed to resolve a control problem of a robot. The technique followed and the way it is implemented may have a significant influence on the robot performance. For instance, the need for continuous motion differs from that allowing a point-to-point control where only reaching to the final position is of concern. On the other hand, the mechanical design of a robot has an influence on the kind of control scheme utilized. For instance, the control problem of a Cartesian robot is substantially different from that of an anthropomorphic articulated robot. As in the latter case, transformation of the end effector motions need to be converted into the joint motions. The driving system of the joints has also an effect on the type of control strategy to be used. If a manipulator is actuated by electric motors with reduction gears of high ratios, the presence of gears tends to linearize the system dynamics. The effective mass and inertia terms of the links are greatly reduced typically by the square of the gear ratios. Hence, the joint dynamics are decoupled and each joint can be controlled independently. The presence of gears, however, introduces friction, gear train compliance, and backlash. As a result, the control designer has to pay more attention to these effects rather than to the non-linear inertia or Coriolis forces, etc., for the achievement of high performance. On the contrary, direct drives, as in the case of direct drive robots, eliminate the drawbacks of gear train but introduce the non-linear terms due to the couplings between the links and joints. As a result, different control strategies, for example, computed torque, etc., must be thought of to obtain high performance. As indicated in figure 10.1, the manipulator control problem is a multi-input, multi-output, that is MIMO problem. To simplify the problem, each joint is considered to be independent and separately controlled. This is generally acceptable for high-geared industrial robots as mentioned above. Hence, each joint is a single input, single output system. The control designed for such a model is commonly termed independent joint variable control, and for an n-jointed manipulator, n-independent CISO control systems need to be designed. Since each CISO system can be modeled as a linear second-order differential equation, its characteristics are studied in the next section, whereas different ways of control it are listed below. Now, different ways of on-off or two-step control. Then proportional control or P control, it produces a control signal proportional to the error between the desired and actual motion, namely the joint positions. Then derivative control or D control, here a control signal is generated proportional to the rate of change of position error. Derivative control is known as an anticipatory control that measures the existing rate of change of error, anticipates incoming larger error and applies correction before the larger error is arrived. Derivative control is never used alone. Then integral control or I control, it produces a control signal proportional to the integral of errors accumulated over time. This type of controller can be considered as looking back, summing all the errors and then respond. In combination modes, in these modes, the above strategies such as proportional, P derivative D and integral I controls are combined such as PD or PI or PID. Now we will see proportional, derivative and integral control of a moving block. In this section, an illustration of feedback control using the damped spring mass system as shown in figure 10.2 is provided. See that this is the spring mass system. This is the mass or block M. It is attached to the spring. Spring is fixed. One end of the spring is fixed, other end is attached to the block M. Now, since this force is applied F to the right side, this block will move towards right side, and when this block will move towards right side, the spring will oppose resistance to its compression. Therefore, spring force will act towards left side, and also here damper is there. Damper they are not shown. Therefore, damping force will also act towards left side because F applied force acts towards right side. Suppose that the natural response of the block is not as desired. Perhaps it is underdamped and oscillatory, and one likes it to be critically damped. It may be possible that the spring is missing altogether, that is, K is equal to 0. So the system never returns to X is equal to 0 once disturbed. Through the use of sensors, an actuator, and a control system, one can modify the system's behavior. As shown in figure 10.2a, one can modify the input force F in a manner so that the desired behavior, say critically damped, for fastest transient response is achieved. It is now assumed that there are sensors which are capable to detecting the block's position and velocity. A control law is then proposed which computes the force and should be applied by an actuator as a function of the sensed feedback, that is F is equal to Kp into bracket xd minus x plus Kv into bracket xd dot minus x dot, equation 10.77, where xd and xd dot are the desired position and the velocity of the block. If the block has to be maintained at rest in the origin, then xd is equal to 0, therefore x dot d is equal to also 0. The control layout is depicted in figure 10.20. Therefore, this is the control layout. See that? Now, how to read this? This is the desired reference. X d double dot means angular acceleration or acceleration, sorry, only linear acceleration because x is linear variable. And this is the summation, summing point is there. Now this control input F is provided to the system. Therefore, system means that block will be displaced by displacement x dot is nothing but velocity. Now same again, x dot is taken feedback signal. Here summation is there. It may be plus or minus. It is multiplied by x. Therefore, x dot into kv, and here x into kp. Here xd is input. Here x dot d is input here to this. Therefore, This is nothing but a feedback control system. The controller reads sensor input and writes the actuator output commands, where x double dot d represent the desired acceleration, that is also taken as 0, that is x double dot d is equal to 0. Note that the left of the dashed line in figure 10.20 is the control system usually implemented in a computer, whereas the right of the dashed line is the physical system. See that 10.20. This is left side control system, left side physical system. Implicit in the figure are the interfaces between the control computer and the output actuator commands along with the input sensor information. The proposed control system is a position regulation system. It simply attempts to maintain the position of the block in one fixed place regardless of disturbance forces applied to the block. By equating the open loop dynamics of the block with the control law of equation 10.77, the closed loop dynamics is derived as mx double dot plus bx dot plus kx is equal to minus kpx minus kb into x dot, or mx double dot plus b into bracket b plus kb into x dot plus k plus kp into x is equal to 0, which yields mx double dot plus b dash x dot plus k dash x is equal to 0, where b dash is nearly equal to b plus kb and k dash is equal to k plus kp. Now joint controllers. Here in this section, what is known in control literature as set point tracking is presented for the feedback control of a robotic joint with the help of proportional and derivative, and proportional, integral and derivative gains. Such control is sufficient for robots without fast motion, especially in robots with large gear reduction between the actuators and links. Now, next method is force control. In many tasks, for example, cleaning of a glass, the robot should not exert more than certain force in order not to break it. In other instances where robots and human beings are working together, a robot must stop when it is touched, that is, a threshold value of force is crossed to make the environment safe. In applications where the end effector has to apply a controlled force, for example, on a glass which is cleaned by a robot, the position control schemes presented in the previous sections will not be appropriate unless the tool at the end effector is sufficiently compliant. For example, like a sponge, if the end effector is rigid like a scraping tool, then any uncertainty in the position of the glass surface or the positional error in the end effector will either cause the glass to break or the scraper will not touch the glass at all. In such situations, the force nor the position should be specified in order to obtain satisfactory performance by the robot. In fact, the robot motion can be subdivided into gross and fine motions. While the former is usually fast and generally should be used for position control, the latter is slow when the end effector's position relative to the environment is accurately adjusted based on force, which could be either implicit or explicit based on an external force or torque sensor fitted at the wrist before the end effector. Since the force control is generally slow, non-linear dynamics of the robot is of little importance. An approach to maintain an interaction force between a robot and its environment is by introducing some kind of compliance into the robot. If this compliance is large, a small position error will cause a small change in interaction force. A special passive compliance device, for example, remote center compliance, can be placed in the robot's wrist to control the applied forces onto the environment. Such devices help in automated assembly, for example, peg in hole or grinding tasks. Passive compliance devices can be undesirable as it may lead to oscillations if the manipulator moves very fast. Alternatively, it is possible to introduce compliance by reducing position feedback gain, which is referred as active compliance. In this case, a small manipulator displacement will cause a corresponding small variation in the control torques. Unlike mechanical compliance, as in the case of RCC, such artificial compliance is software adjustable depending on the specific task. Controlling end effector wrenches through the joint actuator torques is known as implicit force control. Here, position error is related to the contact force through a mechanical stiffness or impedance with adjustable parameters, that is mass, damping ratio, and stiffness of the system. A robot under impedance control is equivalent to an equivalent spring mass damper system with contact force as input. One can, however, use external force or torque sensor to measure its output to feedback in the drive control system. Such control can be referred to as explicit force control. In order to control a force, which includes moment and force both, at the end effector, one may do it indirectly or directly. While the former may be through what is referred in the literature as impedance control, that is maintaining relation between the external force and the robot's motion. The latter actually tracks the forces based on explicit measurement of it as an admittance or hybrid control. If a detailed model of the environment is available, a preferred strategy is hybrid control, which aims to control position along the unconstrained directions and force along the constrained task directions. Okay, we'll stop here.